Hi everyone, I'm Ryan, and today I'm going to be introducing a new unified approach for addressing a broad class of mixed integer optimization problems with logical constraints. And just briefly, this is joint work with my colleague at the OSE, Jean Porphylet, who's going to become an assistant professor at LBS in the fall, and our advisor, Dmitry Butsimas. To begin, let's define the problem setting. In this work, we consider a broad class of general mixed integer optimization problems with logical constraints. Namely, we consider optimizing over binary variables z and some set mathcal z and continuous variables x, which are linked via logical constraints of the form xi equals 0 if zi equals 0. Let's go through the different elements of this problem. Firstly, we have the set mathcal z, which defines the feasible set of binary vectors. So for instance, in many sparse problems, we have a cardinality constraint. So in this case, we would simply require the sum of z's is less or equal to k. Additionally, this framework allows us to model convex constraints. In particular, we can say that x is a member of some set, mathcal x, if and only if g of x is finite, by saying that g of x blows up to plus infinity if it's not a member of this set. And additionally, we have a regularization term to drive the tractability of the problem and convexify the logical constraints. It's always going to be either A, a big M penalty, omega of x is 0 if the infinity norm of x is less than or equal to m, and plus infinity otherwise, or B, a ridge regularization penalty. Now, as a result, this is a very broad framework. In particular, the framework successfully models sparse regression, or best subset selection, network design, facility location, and sparse polynomial selection problems. And moreover, and this is actually a very recent result, we've also discovered that it successfully models sparse PCA, because there is in fact an exact mixed integer semi-definite reformulation of this problem. Now, sort of the main motivation behind this work is the following. There have been a number of works which have proposed exact methods or near exact methods for solving the problems I've just listed here. But a frequent drawback in these exact methods is that they simply don't scale to problem sizes of practical relevance. For instance, existing works on sparse regression, as of the time this paper was written, typically weren't able to scale to problems with more than a couple of hundred features. And this is a drawback because exact methods need to actually be able to solve problems with hundreds of thousands or millions of features, rather than hundreds of features. So that's really where this work comes in. In this work, we make two fundamental sets of contributions. The first set of contributions is a set of modeling contributions. Namely, we propose a paradigm shift. We recognize that the well-known Big M trick, which is typically taught in first-year integer programming classes or optimization classes, is actually the interaction of logical constraints with regularization. Or in other words, that a constraint that x is less than or equal to mz holds if and only if x is less than or equal to m and x equals 0 if z equals 0. The reason this is a paradigm shift is the following. In addition to having x less than or equal to m, we could have a different constraint instead. So for instance, in particular, rather than having such that the infinity norm of x is less than or equal to m, we could simply impose a ridge regularization term in the objective, which turns out to be a viable and often more scalable alternative. Finally, we recognize that logical constraints are actually enforced via a nonlinear reformulation, namely substituting x times z for x to model the constraint x equals 0 if z equals 0. That's the first set of contributions. The second set is algorithmic. Namely, we propose an exact method for solving this class of problems. By invoking strong duality, we reformulate the problem as a min-max saddle-point problem, which is amenable to an outer-approximation procedure. Additionally, we've derived a class of approximate methods by randomly rounding Boolean relaxation. And finally, and most importantly, our approach is scalable. Among other problems, our approach successfully solves sparse regression problems with hundreds of thousands of covariates, sparse portfolio selection problems with thousands of securities, and network design problems with hundreds of nodes. How do we do that? Using our unified framework. Now, in this framework, perhaps the single most crucial part is the Saddle-Point Reformulation, or our saddle-point formulation of the problem. So I'm just going to briefly go through how we get there. So if you'll recall the problem which we had way back here, in this problem, the really challenging part is actually picking the right choice of z. If we know what z is, then picking x is fairly easy. We can simply solve a convex optimization problem in x. As a result, we're going to rewrite the problem as minimizing over the set z in mathcal z, f of z, where f of z is exactly what you want it to be. Secondly, we're going to apply a nonlinear reformulation of logical constraints. Namely, we're going to recognize that the constraint x equals 0 if z equals 0 holds if we replace z times x for x. After we do this, we're going to invoke strong duality to rewrite f of z as a maximization problem, where h of alpha is essentially the Fenchel conjugate of g of x. The exact details of it are in the paper. Now this formulation achieves two things. The first thing which this achieves is that it verifies f of z's convexity, by in particular rewriting f of z as the pointwise maximum of functions which are linear in alpha. The second thing which it achieves is it allows us to achieve a piecewise linear lower approximation of f of z very cheaply. In particular, let's say we pick f of z at some point and we optimize for alpha at that point. We then actually have a valid first order underestimator of f of z for every feasible z. This leads very nicely to a tractable Outer-Approximation method. Namely, we can iteratively refine this piecewise linear lower estimator by optimizing over it and then imposing another part of the approximation. And we can actually implement this using lazy constraint callbacks in C-Flex or Gurobi. And this is actually very nice to do. For something like sparse regression, this will take at most like 50 lines of code to write the entire thing. Now, moreover, while this method is very efficient by itself, we can make it substantially more efficient than this. The way in which we do this is twofold. Firstly, we can warm start the lower bound. The way in which we do this is by running an Outer-Approximation method on this problem's continuous relaxation. And moreover, we can warm start the upper bound by randomly rounding the continuous relaxation in a method I'm just about to discuss. Specifically, we can relax the constraint that z is in some set mathcal z, which is merely requiring that z is within its convex hull. After we do that, we can then minimize this or solve this problem to get a solution to the relaxation. You could do this by either reformulating it, taking the dual again with respect to alpha, and then solving a linear or second order cone problem, or you could simply apply a cutting plane method like the in-out method on the convex relaxation. After we do that, we get some solution z star, which in general will not be integral. Therefore, we can randomly round it by saying that zi is distributed according to an independent Bernoulli distribution zi star. And it turns out that if we do this, then we can show that with high probability, the gap between this solution and the solution to the convex relaxation is actually very small in terms of objective value, which means that in particular, we've obtained an epsilon optimal solution to the overall problem as well. Now this is all very well and good, but sort of the main question which you need to ask at this point is how does the method actually perform on real data? I think this is sort of where the approach really comes into its own. So the first sort of experiments I'm going to talk about is sparse empirical risk minimization. In this problem, evaluating f of z can be done in closed form for sparse regression problems. As a result, our approach is able to scale to problems with hundreds of thousands of features. Moreover, for sparse classification problems, f of z is cheap to solve, which means that our approach scales to problems with tens of thousands of features. This constitutes a 2 to 3 order of magnitude improvement over the set of the art. And additionally, I'll just point out that if we give up on exact optimality, and we're okay with approximate optimality, then we can actually scale to problems with millions of features quite often. And the code for this is available on GitHub. Second set of experiments I'd like to talk about is sparse portfolio selection. In this problem, there have been a lot of existing approaches which quite often rely on things like STP to be able to solve the problem to certifiable optimality at a reasonable scale. Now these approaches are very elegant and often they work quite well, but sort of because they're underpinned by STP, they're sort of limited in their scalability to the size that STPs themselves can be solved. In our case, we're able to obtain similarly typed sort of formulations without resorting to STP, which means we're able to scale to problems an order of magnitude larger. And again, the code is publicly available on GitHub. Additionally, we're able to solve network design problems with hundreds of nodes to certifiable optimality or near optimality, which is an order of magnitude improvement over the state of the art. And recently, we discovered that because Sparse PCA admits an exact MISTO reformulation, we can actually use this approach to deal with Sparse PCA as well. Moreover, by using ideas like the Schur complement lemma and linear algebra techniques, we're actually able to evaluate f of z and its subgradients using simple linear algebra techniques. What this means is that we can solve Sparse PCA problems, certifiable optimality with hundreds of features, or to certifiable near optimality with thousands of features. And we're hoping to have a paper on this on arXiv relatively soon. So to wrap up, the main message of this talk is that you shouldn't feel married to the big M paradigm, because in this work, we've provided a nonlinear alternative which is viable and often more scalable, namely substituting x times z for x and imposing a ridge regularizer. Moreover, by using strong duality, we've derived a Saddle-Point Reformulation, which is exactly solvable via Outer-Approximation. Or you can use randomization and solving convex relaxation to obtain certifiably near-optimal solutions at even larger scale problems. And finally, and most importantly, our approach is both scalable and broadly applicable. So thank you for listening. Just one last note. Thanks very much to the organizers for going ahead with the conference. I know that times right now it'll be very easy to cancel this conference, but this is a great opportunity for students to be able to get feedback. And so I'm very thankful that organizers have chosen to go ahead with it, albeit online. Thank you very much.